And today I'm going to talk about our work, SketchLib. SketchLib helps developers get efficient hardware realization of sketches with minimal effort. This is joint work with Microsoft Research, Boston University, and CMU. So sketches or sketching algorithms are becoming more and more popular to implement network monitoring systems due to its resource efficiency and high accuracy. Moreover, there are many recent works talking about its promising feasibility of sketches on programmable switches using languages such as P4. So many people have the impression that sketches can be easily implementable on programmable switches. However, it turns out that actually it is challenging to make sketches feasible on programmable switches. So let's think of this scenario where you are a P4 developer and you want to run sketches on programmable switches. You found some popular sketching algorithms with working sketching code for the CPU environment. For example, there are C++ sketch code or P4 sketch code running on the software setting, such as behavior model. Then you implement the P4 sketch code for the hardware target. So because P4 sketch code for the software setting cannot be directly compiled for the hardware target, so a little code change is required, and you expect that everything should work fine. However, when you try to compile the P4 sketch code on the switch, you see this compilation error saying switch is out of available resources. So what is going on? This is the exact problem why we started this project SketchLib. So there is a gap between sketch implementations and programmable switches. So first, programmable switches have tight resource constraints, and compiler rejects the P4 sketch code if the resource usage of the code exceeds the limit of available resources. Thus, sketch implementations must be resource efficient. However, it is difficult to program resource efficient code for programmable switches because it requires a detailed understanding of how sketch implementations put burden on programmable switches, and we need to figure out a way to reduce resources without affecting the accuracy of sketches. So the question here is that, can we bridge this gap between sketch implementations and programmable switches? And the answer is yes. Our work SketchLib bridges this gap by providing resource optimizations and APIs. So the contributions of SketchLib are as follows. First, we identified 4 resource bottlenecks across the sketches. And based on this bottleneck analysis, SketchLib provides 6 optimizations that reduce resource bottlenecks by up to 96%. And this makes previously infeasible sketches become feasible without accuracy degradation. And finally, SketchLib provides API to P4 developers, and using API calls will automatically optimize the P4 sketch code. So this is the outline of the talk, and let's take a look at bottleneck analysis. So in order to bridge the gap between sketch implementations and programmable switches, we want to perform bottleneck analysis to figure out the root cause of the problem. Then we ask 2 background questions. The first question is, what are the common operations of sketches that incurs a bottleneck on programmable switches? And the second question is, what are the hardware resources that needs to be allocated to run common operations of sketches? So we will take a look at these 2 questions step by step to figure out bottleneck resources. So sketches have 4 common steps: flow key extraction, hash computation, counter update, and tracking heavy flow key. So for the flow key extraction, Sketch extracts flow key by predefined definition of flow, such as source IP. And using this flow key, Sketch performs hash computation. And using this hash value, Sketch updates counter into the counter arrays. And finally, Sketch maintains heavy flow key typically in a heap data structure. And there is a notion of single-level sketch and multi-level sketch. So multi-level sketches are composed of multiple single-level sketches. Then let's take a look at background on the programmable switches to see how sketches impose bottlenecks on them. So for our work, we use Tofino programmable switch. And programmable switch has pipeline stage architecture, and each pipeline stage has a limited amount of resources for sketches. So if we take a look at per stage resource, there is a hardware called hash call, which can execute one hash computation. And for the memory space, we have few megabytes of SRAM and TCAM. And there is also hardware called SLU or stateful ALU. So it is in charge of read and write operation to SRAM. So basically, it handles memory accesses. So hash computations in sketches require hash call allocations. And counter updates in sketches require SLU allocations. And because sketches need many hash computations and many counter updates, these two resources, hash calls and SLUs, will become bottlenecks. And also, it is difficult to implement tracking heavy flow key in the switch data plane because heap data structure is too complex to realize in this pipeline stage architecture. Thus, resources for tracking heavy flow key is another bottleneck. And finally, the number of pipeline stages is also bottleneck because some sketches have long dependencies in their P4 program, and they cannot fit into this pipeline stage architecture. In the next slide, we will take a look at bottleneck analysis result for two bottleneck resources, hash calls and SLUs. So this is the bottleneck analysis result for hash calls and SLUs. And for the x-axis, it's one of sketch parameters, number of counter rows. And higher counter rows is desired because it can achieve higher accuracy. And for the y-axis, it represents required hash calls and SLUs. So you can see that required hash calls and SLUs can be up to 250 or over 100. And these scales of hash computations and memory accesses are not feasible on today's programmable switches. So our goal is to reduce these bottleneck resources to make sketches become feasible and also save resources for other in-switch applications. So let's take a look at optimizations and SketchLib APIs. So this is an overview of our optimizations and SketchLib APIs. So we identified 4 resource bottlenecks, and we have optimizations for each bottleneck, and also corresponding SketchLib API calls. So for optimization 4, we don't have SketchLib API call because it is optimizing sketching algorithm itself. And for this talk, we are going to look at 2 optimizations, O1 and O5. So for optimization 1, it's reducing hash calls. And to understand this optimization, let's take a look at 3 inputs: flow key, seed value, and bit length. And let's focus on the third input, bit length. The insight of this optimization is from the domain knowledge that many sketches use short bit hash calls. Then it is wasteful to use many short hash. It is wasteful to use many hash calls to generate short hash results. Instead, we can repurpose one hash call to compute long hash result, and then chunk it up to get many short hash results. So by doing this, you can achieve 3x improvement of hash calls. One thing to notice here is that the hash calls between before and after optimization can be different. However, this optimization preserves accuracy because hash independence among bits in long bit hash result is well maintained. And also, there is one condition that must be met when we want to apply this optimization. It is flow keys for 3 hash calls must be the same. And let's look at the next optimization. It is reducing SLUs for multi-level sketches. So recall that SLU is a hardware that is in charge of read and write operation and handles memory accesses. So SLU must be attached to each 1D counter array. And in this example, we have 3 counter arrays per level, and we have 3 levels. So we need total 9 SLUs are required. Then one property that we can leverage from the sketch design is that many multi-level sketches, only one level needs to be executed. So what we can do here is that we can consolidate many short counter arrays into one long counter array and assign only one SALU to it. So this optimization is possible that we know that only one short counter arrays across levels need counter update per packet. So in this way, we can achieve 3x SALU improvement. And also, there is no behavior difference between before and after optimization. Thus, we don't need to worry about accuracy changes. And then we'll take a look at end-to-end code example to see how we can use SketchLib API. So you have this one example of UniVMon P4 code example. And what you can notice here that, as we saw in the previous slide, you see this inefficient of many hash calls, and also inefficiency of SALU allocation. So you know that you can apply SketchLib optimization. Then you go to the SketchLib, and you found these 2 API calls for corresponding optimizations. So now what you can do is that you just need to replace previously inefficient code with SketchLib API calls. Then now your code is automatically optimized, and bottleneck resource will be reduced. And this shows a generality of SketchLib. So we have 15 popular sketches from different venues. And at the last column, you can see that we can apply many optimizations to 15 sketches. So overall, SketchLib can benefit a broad range of 15 sketches. And also in our open source repo, we have full implementation of all 15 sketches. So let's take a look at evaluation. So SketchLib reduces resource bottlenecks significantly. For the x-axis, we use 7 representative sketches for this resource reduction evaluation. And for the y-axis, it shows percentage of resource reduction between before and after optimization. So if you take a look at one example of single-level sketches, counter sketch, we can see that SketchLib reduces 31% of hash calls, 0% of SALUs, and 9% of pipeline stages. And if you take a look at one example of multi-level sketches, UniVMon, we can see that SketchLib reduces 91% of hash calls, 90% of SALUs, and 65% of pipeline stages. So you can see that overall, SketchLib reduces resource bottlenecks efficiently across all 7 sketches by up to 96%. And this will make previously infeasible sketches feasible. Then let's look at the evaluation that, and I want to say SketchLib preserves accuracy. And for the x-axis, we have 5 different data sets for sketch results. And they are CAIDA ISP traces from different date and time. And for the y-axis, it shows percentage of error. And for the blue bar, it means accuracy result for before optimization, and we call this software baseline. And for the green bar, it means accuracy result for after optimization, and we call it SketchLib optimized on hardware. So we can see that across all 5 different data sets, the accuracy is similar between before and after optimization, meaning that the difference of median error is less than 1%. So for the conclusion, the promise of Sketch today is still unrealized, and SketchLib helps developers optimize Sketch implementations on programmable switches with minimal effort. And SketchLib is general across sketches. It can benefit a broad range of 15 sketches. And our SketchLib is fully open sourced. You can find API calls and also a full implementation of 15 sketches in there as well. Thank you so much.